is to just let everybody know where the technology is at, how it works, and how, as an industry, we can utilize this to make progress, because I think it's going to be one of those technologies that'll continue to move us forward. We're going to get kicked off with Dr. Dave Faber. Many of you know and have heard of Transova Genetics, but he is the founder. Started out of his garage with the technology, and has developed it into a company that is massive, and the technology and what they've been able to develop. And Dr. Faber will kind of lead us off with the information and how everything's evolved over time relative to advanced reproductive technologies, and kind of the fears that everybody had relative to AI. And talking to some of the older Hereford breeders that we have, they were concerned about AI and the use of that in the early days, and we've been able to overcome that. And so I think there's some parallels that he can draw, and that's definitely a technology that, as we learned last night, that can help us get there. Dr. Allison Van Neenem is going to speak as well and get into a little bit more of the specifics around the technology and her experiences with that. And then next we'll follow up with Dr. Tad Sonstergaard. He is the CEO of Excelligen, and that is one of the companies, one of the premier companies that offers this technology, and is the one that can kind of help producers. He can take it to market. And then we're going to close. I called him the closer, Dr. John Beaver. And many of us know Dr. Beaver, good animal breeder, and has been in the industry for a long time, and has served some leadership roles relative to gene editing. And so it's a great panel. With that, I'm going to turn it over. We'll answer questions at the end. We'll let these panelists kind of give their take on gene editing and where we're at, and then we'll do a Q&A right after that. Floor is yours, Dr. Faber.
All right. Well, thank you. Certainly appreciate being able to be here to speak today. And I thought, Allison, you did a nice job last night of kicking this off and talking about gene editing. And I've been asked to talk about some of the history and evolution of some of the reproductive technologies, and these all tend to fit together. They're complementary pieces, so to speak. And so to look at maybe some of the history maybe helps us look forward even to some of the things from a future standpoint. And so what I've got in the very first slide is Transova's developed what we think is a world-class toolbox of reproductive tools: embryo transfer, in vitro fertilization, sex-sorted semen, genetic preservation, services, both doing genetic engineering work in the biomedical space, but also then services for genetic engineering groups. And in reality, these are all things that have developed, and they're part of a continuum that I've been lucky and fortunate to be able to work with over these years. And I think that, Mark, I think the bio that I sent in was actually one that was about 20 years old. Unfortunately, I must have attached the wrong one, but maybe that was wishful thinking on my part, because I wish I could have another 20 or 40 years to look at what other technologies will come. And one of the concerns is, as we start to stop some of this continuum, then what do we stop in the future as well? And so, again, looking at the continuum of reproductive technologies, and in reality, that toolbox, if you can go to the next slide, in reality, that toolbox is designed to create genetic gain for farmers and ranchers. And if you look, I had one of our geneticists plot the genetic value, or the net merit index, of Holstein cows. We do about 40% dairy work, about 60% beef work, and the dairy work gives us some pretty good measuring sticks. And so the net merit dollars is an index that not only measures productivity in terms of milk and components and proteins and those things, but also productive life and fertility and things. It's a profitability type index. And if you hit the next slide, please. Go one more. So this is the slide I'm referring to. And hit next again, please. And you'll see at about 2012, there's actually an inflection point that starts to happen. And what you've got in 2012 is an increase that we went from bulls that were at about $20 per year improvement year after year for a period of time. And then subsequent to that, it's jumped all the way up to about $80 to $85 of genetic improvement. And so what really caused that? If you look at the next slide, and if we look at the number of embryos that were produced during that time, you'll see that it actually mirrors that. And we were going along producing about 45,000 IVF embryos a year, primarily for the beef industry. And then the dairy industry really started to utilize our technology, partially because of the genomics that came along that increased accuracy, but also our performance on number of embryos for ovum pickup greatly increased. So increasing numbers of ovum pickups, increasing embryos per ovum pickup made it more affordable, more enhanced the selection intensity further, and so you can see that it almost mirrors that improvement in genetic gain in the dairy industry. Let's go to the next slide. All right, and if you look at if you look at some of the various technologies and things that are there, you've got artificial insemination in the lower red line, you've got in vitro fertilization then above it, then using techniques such as laparoscopic ovum pickup are techniques where we actually go to younger heifers. Allison, you showed pictures of sheep yesterday where they did surgeries, and we'll actually use a laparoscope to harvest oocytes from 2 to 3 month old heifer calves, and we can turn generations more quickly and have more impact. And then there's technologies that in the future, for example, with stem cells, that have the ability to do true in vitro breeding that would greatly enhance even further the genetic gain. Next slide. All right, and so now we'll take a look back and look at maybe what history has shown us and where we can maybe where we can go with this in the future. And so I went all the way back, and Jack actually asked me to do this for the Hereford Association, take a look at it. My first thought was I'd rather talk about the right side of this and the new innovations and things in the history, because I'm not a historian by nature. I want to be over on the right side of these charts. But if you look at artificial insemination, it's interesting. Shane, you mentioned this from an acceptance standpoint, but in 1694 was really the discovery that the sperm delivered the conceptus, and that it wasn't quite accurate because they believed that the little baby was actually curled up in the sperm head, and that's how it was delivered. And I wonder what things we know today that we think are absolute truths we'll find out 40 or 100 years from now perhaps weren't. But then it was used in some various species and things, and then in about 1990 there was some artificial insemination in Russia and Denmark. Then you had events that were really accelerators. So you had discovery events, and then you had accelerators. And accelerators like semen extenders, antibiotics for the semen extenders, the first frozen calf being born in 1952. Then you have logistical things that happened, like liquid nitrogen tanks, so that you could transport and store semen on farm. And those were ones that were really breakthroughs. I think ABS actually developed those. And those are the things that were really the accelerators. So you have discovery events and you have accelerators. And today there's 264 million units of semen being utilized in the industry. Next slide. All right, in vitro fertilization in a lot of ways is much the same, but a compressed timeline, which makes sense as we move forward. Things are happening faster and faster with science and technology, so a more compressed timeline than what we saw with artificial insemination. But the birth of baby Louise being the kind of a landmark breakthrough event, so to speak, and the first in vitro calf being produced in Dublin from an abattoir-derived oocyte. And then our very first calf was born in 1992 from a transvaginal aspiration, exactly the way we would do it today. Although we weren't very good at that time. I mean, we produce about a half an embryo to 1 embryo per ovum pickup attempt. And over time, the accelerators we got better. We developed media so we could ship oocytes and embryos around in portable incubators, similar really to the AI story. We improved the media, we improved the results and performance. And so over a period of about 30 years, it has went from a concept or an idea to where we're on track this year to produce 650,000 IVF embryos, which I would have never thought was a number that we would hit. Although if you think about the power of an embryo bringing both male and female genetics, it's got that type of potential to have a significant impact. We'll go to the next slide. And then likewise with cloning, and cloning really fits really nicely in and is a complementary piece to what Allison talked about yesterday, because we'll utilize cloning, works very nicely to produce gene-edited animals, for example. And the breakthrough event that people think about are usually is the birth of Dolly the sheep. And if anything, I wish that one wouldn't got as much publicity as it did, because it shined a really strong light on it and technology and a lot of questions and things from that standpoint. But actually, there were discovery events that happened before that of a frog being cloned to a tadpole, for example, in the 50s, a species that's maybe more adaptable to cloning techniques, for example. And then the use of blastomeres, or cells from an embryo, to be able to do cloning, or embryo splitting, where we actually would bisect an embryo and produce an identical copy with a different technique or a different approach. But then really the breakthrough events occurred after that time, and around 2017 was kind of a red letter year for us at Transova, in that at about that time we went for almost 20 years of having a relatively low success rate, where we'd be 5 to 10% of the embryos we would transfer would make it all the way through gestation and turn into a healthy, happy calf. And starting in about 2017, 18, 19 were the periods we've jumped that up, and we've kind of leveled off again now, but leveled off around 18 to 22 or 4%, depending on the breed, particularly, of what kind of success ratios we'll expect. Also in that year, we produced clones from embryonic stem cells, and we'll talk about that a little bit later, and the importance of that and how that fits into things that we can work with Excelogen and Dr. Sansegard on, in terms of the ability to move forward with the gene editing programs. Next slide. And then I think this one's has been nicely covered, Allison. I think you did a really good job of talking about some of the background and history. Our very first genetically engineered calf was produced in 1996, so we've been at this for a long time. And primarily all the work we did was in the biomedical space. We also then started producing a lot of pigs for both ourselves as well as some other companies for disease medical models and for xenotransplantation, and continue to do a lot of that work today. Let's go to the next slide here. And to illustrate, you have discovery events, and then you have to go through maybe some accelerators. Our very first calf that we produced was done by a technique called microinjection. And that particular calf, we superovulated 2,000 Holstein cows. We recovered 15,000 one-cell embryos that we microinjected. If you look closely in the screen back behind Esmail, it's doing the microinjections. You can actually see the needle, very similar to what you were showing last night, Allison, other than this is before CRISPR-Cas9. And so the construct would go in, and we'd cross our fingers and hope it integrated somewhere, and somewhere that was a good place, as opposed to what can be done today. And so a lot of accelerators coming on both the genetic engineering side of things as well as the technologies. And from that, we produced 500 pregnancies in one transgenic bull. So at that time, that may have been the most expensive animal produced. Let's go to the next slide. All right, and then we also worked on projects where we actually tried to do multiple genetic modifications to produce cows producing human antibodies. There's a company called Kirin, and a company today now called SAB that's publicly traded, who produced humanized antibodies, where we had to make multiple knockouts and knock-ins of genes in order to accomplish this mission. We literally spent a decade or longer doing this, because we'd have to make a modification, then get to either the fetus or the next generation, and do the next one and the next one. And today, work we can do with, and that Dr. Sansegard can do, accelerates this very quickly. Let's go to the next slide. And one of those things is the breakthrough of being able to use embryonic stem cells. And By embryonic stem cells, we're talking about taking over on the upper left, a day 7 bovine embryo, and the little disc at the bottom, as it's called the inner cell mass, that actually becomes the calf. The cells around the outside become the placenta. But culturing that inner cell mass and turning that into a cell line allows us to do a couple things. One is we can test that cell line genomically and know that it is a true outlier or a really good high-quality genetic line of which to do our modifications in. And then that can be targeted by an outside group, returned to us, and then we can utilize cloning to produce a calf. And so basically things that took us a decade before, Excelogen is able to do literally in, a year, Tad, or a year and a half, accomplish those type things. Next slide. And in reality, we spent most of our time working in biomedical applications, but I'm a farm boy by heart, and I was looking at this thinking in 1997, in 10 years, we'll be probably doing this for agricultural purposes, and that's a lot of why we looked at and worked in the biomedical space, and we continue to today. But I was clearly naive from the standpoint of what kind of things we would do and when we would do it, and from an acceptance standpoint. And I'll let Tad talk to some of the projects that are ongoing, but we'll work a lot with Tad and Excelogen. We'll work a lot with other groups, Beat Animal Research Center, et cetera. Okay, next slide. And one of the things that we know is that from an acceptance of technology standpoint, I was naive from that standpoint that and if we look back, and Shane, you mentioned this, that almost every step of the way they've questioned whether it's reproductive technologies or others. Things like, is it fair? Are you playing God? Is it natural? Is it going to be available only to large producers and large operations and things from that standpoint? And those aren't new questions. You mentioned it from artificial insemination. I clearly heard it during the years of starting embryo transfer. We've heard it with cloning. We've heard it with things we're doing with genetic engineering, for example. And so these aren't necessarily new. But if you go over to the quote on the quote over on the right, it's unknown what long-term health consequences may unfold. Studies are not adequate. Furthermore, this will likely decrease product acceptance and consumption. Will be catastrophic for small farmers. It sounds like something we could have talked about last night or at other meetings, et cetera. But in fact, this is a quote from 1924 following the introduction of the pasteurized milk ordinance. So we've seen these kind of things not only in reproductive technologies, but in other technologies as they're developed, whether it's computers or artificial intelligence right now, for example, you will hear these kind of things. Let's go to the next slide. And then this was a cover of Time magazine. One of my people found this here the other day for this. And if you can hit the next one, and the quote, we're talking about human-animal hybrids, monstrous babies, and reproductive engineering, and which is actually a quote following the birth of baby Louise in 1978, and preceding the birth of over 2 million IVF babies. So again, you see these kind of paranoias and things from that standpoint. I think it's human nature that change equals risk for people and fear from that standpoint. All right, next slide. All right, but just because we can do something doesn't mean that perhaps we should. And so I spend a fair amount of time, and now I'm talking about really my beliefs, and from a Transova standpoint, of course, then the way we look at and how we want to look at things. And I believe that we need to be good stewards. We need to be good stewards of our environment. We need to be good stewards of animal welfare. I learned yesterday from Dr. Roundtree that on the environment, I'm really at, what did you call that, the peak of Stupid Mountain, or the peak of stupid yesterday when you were talking about where it's at. And I think that's where I probably fit the best when it comes to some of these. But that's my belief, that we need to be good stewards of our environment. We need to be good stewards of animal welfare. We need to be good stewards of technology. I understand those are my views, and if you wanted to bring people in from far left, vegan, PETA groups, et cetera, they just as soon not have a cow anywhere on the face of the earth, right? And so I can respect others' thoughts and opinions, and I can respect the fact that the choice is a great thing that makes us a great country, for example, but choice goes two ways, and I want to be able to utilize these technologies. and be able to utilize these things for people that where it's most appropriate. All right, and so what's it mean from my standpoint in terms of being a good steward of technology? It's about the mission of providing opportunity through genetic gain. That's our mission at Transova. And so if we can meet that mission, as well as enhance the protein, the production of high quality, safe animal protein, while improving animal welfare and sustainability. And I think we've got to take all three of those things we want to be, from a Transova standpoint, I believe we must take all three of those. In other words, we can't do something that maybe comes at the cost of animal welfare or the environment or miscellaneous things. If we can improve all of those, I think it has value. If we can produce cows that are heat tolerant or disease resistant or other things that have the ability to improve environment, and we have countries like India with 100 million cows producing less milk than what we do in the United States. And so can we advance genetics and advance production and feed a world? To me, that is being a good steward of technologies and things in places I'd like to see it used. And then the last slide I've got here, the last quote over on the right, is one from Norman Borlaug with the Green Revolution, a fellow Iowan, that the first part of that, I now say that the world has the technology to feed on a sustainable basis a population of 10 billion people. The more pertinent question today is whether farmers and ranchers will be permitted to use this new technology. Exactly what you were talking about last night, Allison, on, will we be able to use it from a regulatory standpoint or social acceptance standpoint, et cetera. But I probably actually relate to the second part of that paragraph, or the second paragraph, which is, while affluent nations can certainly afford to adopt ultra-low risk positions and pay more for food produced by so-called organic methods, the 1 billion chronically undernourished people of low-income, food deficit nations cannot. And so I think that it also points to where I believe we need to be good stewards from the standpoint that it's not just about our own political and economic social status here in the United States, but around the world. How are we going to produce food economically enough and abundantly enough to be able to move that forward? And I feel a calling from that standpoint. So, with that, I want to say thank you, and for the opportunity to be here, and appreciate the ability to speak with a lot of you. So, thank you.
All right, see where I stand and don't get feedback. Can you guys hear me okay? Okay. All right, so Brave, you can, all right, you got it going. So I've been asked this morning to address the current inventory of gene-edited cattle, and I'm going to point to Bray when it's time to move slides. Not working too well. All right. Nope. So last night I spoke about that this editing is a way to introduce useful traits on top of our breeding programs. It doesn't replace breed associations. It doesn't replace everything we do in conventional selection. It's just a cherry on top of the ice cream sundae. Oh, it's working well now. But we've got this regulatory issue, and I'm going to spend a little bit of time today talking about my experience with the regulatory issues, because I think we're going to have more of that discussion later on today, and I just want to give a feel for what it's like to work in this space if the regulations are not sensible or risk proportionate. Okay, and I wanted to just follow up on David's comments pertaining to the two approaches that you can use to basically do genome editing. So one is that you're picking up a cell line from a very elite animal, and you're going to be editing that cell line and then transferring that cell line to an empty oocyte and cloning it. And that has certain advantages because you know exactly what you're going to get when you clone an animal. Every cell is going to be the same. You know what the edits are. The disadvantages historically have been low success rates with cloning, and that maybe is getting to be better percentages, I heard this morning. The other approach is to basically go the route of picking up oocytes and crossing it with the very best males, and then editing that one-cell zygote, or the developing embryo, as I spoke about, which, if you're very lucky, will produce a homozygous non-mosaic animal, and that's the calf over there on the left, the holy grail, which is the dark purple calf with both alleles edited. Or, if you're somewhat lucky, you might get a heterozygous non-mosaic animal that you can then cross, but of course that takes time. But more likely, what you're going to get is a mosaic animal. And mosaicism refers to when there's different cell populations in an animal that have a different genotype. And so if you edit subsequent to that first cellular division, you can get perhaps an animal that's got normal wild type in some of it, and edited lines in other aspects of it. And then you're pretty much in a situation where you don't know 100% sure what's going to come through the gametes, depending a little bit on what actually populated those gametes, and you might get segregation in the gametes, or you might even get really unlucky and it's all wild type in the gametes and you don't get any of the edited cells in those gametes. So mosaicism then is cells within an animal that have a different genotype, and so ideally what you'd like is to get that homozygous edit down the bottom. So if the animal's AA and you edit it, you want the BB animal, and you'd like all cells in that animal to be BB. But sometimes you'll get not only BB, but you might get AC, BC, a range of different edits. And that's one of the disadvantages of actually doing the edits in the developing embryo versus cloning, where you can absolutely categorize what characteristics you've got in that animal because you can sequence the cell line, and then once you produce an animal from that, you don't get any mosaicism. And so there's pros and cons to both of the different approaches. So I just want to go back to the genetically engineered salmon. So here's our friends, the homozyte, or the siblings here, one that's going to get to market in half the time relative to its non-transgenic sibling, and I'll let you guys figure out which is the one that's carrying the transgene in this image. But I want to draw attention to the fact that this paper was published in 1992, last century. And because it was a genetically engineered animal, it had to go through this regulatory approval process with the FDA that took over 30 years. And basically, from the founder event in 1989 to actually getting commercial approval, it was around about 35 years. And if you actually look at what had to be done, the FDA is regulating these as drugs, so you have to show what you've introduced, you have to show that it's what the genotype is, what the phenotype is, whether it's durable, whether it in fact grows faster, and do all of those studies. And during that entire time, none of the animals that you're working with are allowed to enter the food supply unless you get what's called an investigational food use authorization. And so the company that developed the Aqua Advantage salmon, which has the patience of a saint, spent about $20 million just basically incinerating or burying or composting fish, waiting for an FDA regulatory approval for a fast-growing fish. And I want to ask you animal breeders, have we ever developed fast-growing animals in our breeding programs? Like, that's all we do pretty much. Like, a chicken today grows 4 times as fast as a chicken of the 50s. You know, a dairy cow today produces 4 times the milk she did in the 1950s. This is not an unusual phenotype. And what was the unique risk here? I don't know, nothing. But that's what it took to get through. So when editing came along, it's like, yay, we've got this technology where we're not introducing a transgene. Surely we will not be expected to go through a new animal drug approval process. Yeah, no, that's not what the FDA determined. They determined that all intended alterations were going to be regulated as a drug. So I'm going to give you an example here of work from Macy Mueller, who's now an assistant professor at K-State. We basically introduced a knockout in cattle at a gene called NANOS3 using a dual guide approach. So basically she had the little sequences that tells you where to knock out on either side of an exon that knocked out this particular gene. So NANOS3 is one of those germline genes that produced sterile animals. So basically we did exactly the procedure I showed you last night with the sheep, but we did normal embryo transfer to get these animals. We had 3 males born, and what we were wanting to do was to get investigational food use authorization to put those animals into the food supply with the FDA. And so we filed an investigational new animal drug application because we're a public university. We don't need to pay the fees that would normally be associated with that, which a company would have to pay. And we requested this investigational new animal drug authorization. It's only 3 animals, but at the end of the day, at a public university, we normally sell our animals into our meat lab. We sell the meat lab to the public. That brings income back to the university, and the wheels on the bus go round and round. We're not usually diverting them to the incinerator over at the vet school and paying to incinerate them. So it was a little bit to test whether this was possible and also for financial reasons. So we had these 3 calves born during the pandemic, actually, in 2020. So I did an investigational new animal drug food use authorization request for these animals, and this is what we were asked to provide. So a complete description of the animals proposed to go in the food supply. Okay, 3 bulls, infertile, knocked out at nanos 3. That's good. I already collect that data. That's not extra. A characterization of the IGA, intentional genomic alteration, and any intended effects. So yeah, look, here's my gene. I've knocked it out. The bulls are infertile. Nothing else going on. They're running around thinking they're fertile, but they're not. And then any animal health data we get, and we would normally collect just weight data and things like that. We're not typically doing anything more than that. Then compositional analysis. Well, now we start to get into something that we don't normally do. So what is the compositional analysis of the meat from an infertile bull? Well, I would say that's probably pretty similar to the compositional analysis of a steer. That's also known as infertile bull. But we don't actually have any data on that. And so if we have to provide that, we're going to have to kill the animals, which kind of defeats the whole purpose of food use authorization, because by the time we get the data back on the animals, which we did with the polled animals, it's several months later. So if we actually have to provide that in writing, so to speak, that pretty much negates that. But it's this last one that really touches a nerve with me. So we've designed these guides, that is the little guide RNA that tells Cas9 where to cut, very carefully to not have any sequence similarity with any other sequence in the 3 billion base pairs that make up the genome that doesn't have at least 3 base pair mismatches in the 20 base pair recognition sequence that we're targeting in nanos 3. So we're careful in our guide design, and we've done basic research showing that if you design your guides carefully, you have very limited off-targets. And what these off-targets are is sequences that have at least a 3 base pair mismatch with your guide, where potentially you could have a cut with the Cas9. It's hypothetical. And what they wanted us to provide was either sequence data or basically go into each of these target sites, and the target sites are shown here. This is what the FDA gave back to us. Where I say target, that's our guides. That's what we designed, and that's meant to cut on chromosome 7 in exon 1 of nanos 3. So that's the intended cut, and we got that. The other ones, you'll see, have, like, you can't really see it, but there's a little bit of red in them. There's 3 red sequences in there. They're potential off-targets that cut in other regions of the genome. Now, if I'm going to go into those animals and have to either PCR up each of those 10 different sites to determine and ensure we didn't get an off-target, that's going to take work and will cost something, or I have to do sequence data on them, which is all possible, all costs money, and then do a bioinformatic analysis to see whether there's an off-target at these 10 different sites. But I guess more generally, I back up and I go, what is the hazard that we're doing all of this analysis for? Because if you're asking me to do this, there must be something really dangerous about an off-target that's going to be associated with food safety. I can't come up with a single hazard. So am I going to spend time doing this for an investigational animal at a university? No, I'm not. Like, that's not part of my experiment, and I'm not trying to commercialize these animals. I just want food use authorization to put these 3 damn bulls in the food supply so I don't have to burn them. And more generally, if you look at the amount of genetic variation or unintended alterations done by nature, there's literally millions if you look at different breeds of animals. And this is not associated with any food safety concerns. As I said last night, that is the basis of our genetic improvement programs. If there wasn't any genetic variation between animals, breed associations wouldn't exist because there'd be no variation in these animals. And more generally, if you look at going from the 3 billion base pairs that make up the bovine genome, that's the bottom of that pyramid that's shown there, and you work up through the between breed SNPs, you're getting into the tens of millions. If you're looking at the indels between animals, you're getting into the millions. If you're looking at within breed single nucleotide polymorphisms, we're looking at 10 to the 6. Within breed insertions, deletions, 10 to the 5. Parent progeny differences, 10 to the 4. Until you get all the way up to the top, where you have de novo mutations and you differ from your parents by about 10 on average. Just spontaneous, naturally occurring genomic alterations introduced by nature. And that is the reason that we have evolution. All of these are going on in the background of everybody's breeding program, and never do we ever have to document whether those alterations are happening in our food-producing animals. Why the heck would we need to do that now when there's no novel food risks associated with this? So I said no, not doing that. And at the end of the day, we were actually able to get feed use authorization, which means we were able to render these animals so they could get cooked up and go into dog food. So that's better than burning them, I guess. But this doesn't make sense, and I fundamentally reject doing science that has no biological basis. I think it's a waste of public resources, and I refuse to play along with this game because I think the emperor has no clothes on. And I can say that because I'm not trying to commercialize anything. The companies will be more constrained in what they can say, but I think it's stupid. So Washington State University, however, went down this path and played this game with the FDA. So they did a Nanos 2 knockout, which is a similar approach to what I mentioned. They were doing it in pigs, and they said, we would like to put a food use authorization on these 5 pigs to get them in the food supply. And back in 23, there was a great big press release. Oh my gosh, WSU researchers have historic FDA approval for gene-edited pork. Not really, they didn't. They had a food use authorization for 5 pigs where they had done everything the FDA asked, all of the sequencing and what have you, and they got food use authorization to make sausages out of 5 pigs, and it cost them $200,000 to get 5 pigs into the food supply. Was that a good use of resources? I guess Oatly has more money to spend on stuff like this, but to me, that is not a good use of public resources, and I think that we need to push back on silly regulations that don't make any sense. So with that, I look forward to hearing, well, I do want to just say, where does this play in breed associations? So what is the opportunities here? I think that editing offers an opportunity to repair deleterious genetic conditions, potentially, to introduce useful alleles into breed germplasm, currently primarily useful for Mendelian traits, so 1 or 2 or 3. It's not going to necessarily address polygenic traits that are controlled by thousands of genes, so it has a place. It's a cherry on top of the breeding sundae. It doesn't replace the sundae. It could be used to introduce traits that can skew sex ratio, as I alluded to last night. The use by industry likely hinges on having something more sensible than what I just outlined with the FDA's approach. And as I said yesterday, I really think the future of genome editing will be governed by whether we develop a fit-for-purpose regulatory approach that enables safe edits to move into the food supply. And I'm just going to cut it off there and let Tad tell you all the great work that Excelligent is doing. Thank you.
Good morning, everyone. Thanks to the organizers for the invitation to speak. And what I'm going to talk about today is really going from taking a laboratory tool for making experimental animals to how our company has used this tool to commercialize this technology for genetic improvement for food animals, and making that technology available all the way from smallholders to progressive breeders. Next slide, please. So just give you a little background on Excelligen at a glance. It was formed in 2013 as a subsidiary of Recombinetics, whose platform is to do gene editing in livestock cells for both biomedical purposes and also for genetic improvement of food animals. It's mostly been funded by angel investors and non-dilutive capital, which is grants, and we're located in Minnesota. Right now, our company as a whole, the parent is 18 employees, and we have about 8 employees that work within Excelligen. One of the things you have to do if you're going to make commercial animals and have sales, you have to have licenses and intellectual property to have the freedom to operate within the commercial space. So there's a lot of capital that goes into securing these licenses, pursuing these patents, and it goes not just from using the gene editing tools, which were discovered by other universities, mostly for human applications, where most of the capital is being invested, but also the methods for breeding those animals, using those tools, and then also the traits. I think our early history, we've been doing this for more than 10 years, has really been to develop proof of concept traits in cattle, swine, and finfish. So we've made animals in all those spaces. And we're really the pioneer company as far as offering partnerships to beef breeders to access this technology. So our portfolio right now of traits we're actively working on or have introduced into cattle is we can edit at 10 different loci for 8 different traits, and 5 of those are still in pre-commercial. And part of that is because the claims that you make, you have to go through regulatory, and it's probably a much more difficult path, and that requires a lot of capital. So I'll talk about some of those. Go back, please. We do have commercial allowances right now for some of our traits in 3 countries, so heavy muscle, polled, and heat tolerance as in slick, and we've also done semen sales in the US and Brazil, and we actually have progeny on the ground in the US. Next. Next slide. Okay, just a reminder, why are we using this technology? It's really a way to shortcut in a single generation what has been done in the past through admixture breeding or crossbreeding or upgrading. So you have a trait in an animal. In this case, it's an adaptive trait for heat tolerance. You would cross that animal, which they did at like the University of Florida. They crossed Senepol to Holstein, and in the end, after grading up, after many generations, they have a slick Holstein. But the problem with that is that the genomic merit of that Holstein is not very good or very competitive, but it does have that trait for heat tolerance. Whereas in our case, we can introduce that into our elite performance animals, whether it be Angus on the beef side or Holstein on the dairy side, for example, and in a single generation create animals that are founders for these new genetic lines using this technology. Next. So conventional breeding, very costly in time and resources to have that large population to bring that trait in, so you avoid inbreeding, and it's disruptive to selection. Whereas gene editing mimics the natural mutation process, which we can do very precisely and accurately, and it's not disruptive to current selection programs, especially the use of genomic selection now. Next slide. So how do you move from doing experimental animals and really cool things like Allison talked about to commercializing this technology? Next. So one of the things, when I came to Excelligen, of course, I've been in the cattle industry since I was 12 years old. 1976 is when I bought my first heifers. And my passion's always been to how do we breed better animals. So when we had this ability to do genomic selection, you know, we solved a lot of issues as far as being able to predict future generations. But what about all those traits that got left behind in the development of some of our breeds that we want to bring in? And how do we do that and instill confidence in the breeders to be able to use this technology? So here I have a scope of work as to what we do in our breeding platform, and really that first box on trait discovery, IP, and licenses, yeah, we can go out and identify what traits may have major effects on some of the things we care about relative to animal well-being and health. But if you, the producer, don't want them, it's not something that we're going to invest time and money into bringing into those populations. So it really starts with a discussion with the breeders as far as what traits are important to the breed. Then a lot of our time and capital has been spent on optimizing the introduction of these traits and the different reproductive methods that give us the best outcomes. So Allison and Dave talked about some of those technologies, And here I'm showing an example of a timeline of the different animals that we introduced the heat-tolerant slick trait into, which is there's a number of naturally occurrent variants that truncate the prolactin receptor that have been found in the Caribbean basin, and we're just mimicking that and introducing it into these animals. So we've done cloning at fibroblasts, we've done embryo injection, and now we've moved to bovine embryonic stem cell cloning after gene editing. Next slide. Stop there. As part of this, we want to make the process easy for everyone to understand what we did. That includes regulators and the value chain. So we go through a rigorous process that's under a quality control, quality management system to prove that our cells are disease-free. So that means we'll have optimal cloning outcomes. There's no disease inherent in the animals when they're born. The identity is known all the way through the process so that we're not mixing up which animals are what, and making sure that we have good genome integrity and we haven't made any changes we didn't intend for, and the ones that we intended are there. We have to do phenotypic characterization of the animals, not just for the regulators, but also for the marketplace. We have to show that they have vitality and economic value. Next. And so we're demonstrating the product integrity. And then we have to go out and seek not just the commercial license to bring these in, which involves sometimes breed association sanctioning of the trait, but also that social license, not only with the consumer, but the upstream part of the production, the value chain before the consumer. So here's an example of how we have standardized our founder production now. We'll purchase high-value matings. In this case, I'm just showing Angus as an example. And we'll create those IVF embryos, and those IVF embryos will be sent off to Transova, where they make a bovine embryonic stem cell line. Those stem cell lines then come to us, and we'll do genomic testing if the customer wants it. If they don't, we'll just pick one of the cell lines that looks the healthiest in the dish, and we'll do quality control testing for the pathogens and go on to the gene editing treatment. Next. So after we check for cytogenetic abnormalities and on-target editing and off-target editing, we'll send those cells off to Transova for the somatic cell nuclear transfer. And so what's the advantage of these cells? There's longevity in culture. So we didn't have that before with fibroblasts because the cells get sick after a certain period of being in the dish. With the bovine embryonic stem cells, we have a much longer working time, where we can do this estimate of genomic merit through genotyping, and we can also introduce multiple edits, something we couldn't do very well in the fibroblasts before. The outcome is we don't have the mosaicism that Allison talked about, so we don't have to go and breed a second generation from our founder animals in order to go to homozygosity. We can go straight to the market. And we have a higher accuracy because we can pre-select in the dish those cells that have the edits that we want. And if there's any off-target issues, we can look for those as well ahead of time, because that's what the regulator is going to ask. And of course, I just wanted to point out again, this advanced reproductive methodologies is powered by Transova and all of the advances they've made over the years through all of their private R&D funding. So here's an example of an animal that's gone through this process. We purchased embryos from Takeda Farm Genetics. This is a full-blood Wagyu. If you don't know, there are no full-blood Wagyu animals that are polled. So we purchased a number of embryos. We made some cell lines. We picked the best one for this high marbling line. And we were able to create 2 different clones from a single cell line. So these animals are exactly identical. It's just they were born on different dates. The one on the left is already at a stud in collection, and the one on the right will be heading there soon. So they're doing really, really well. Part of our advancement in our ability to do gene editing would include stacking of traits and using of these bovine embryonic stem cells, things that we hadn't done before 2020. And so we were lucky enough to convince the Bill and Melinda Gates Foundation that we could do these things prior to actually doing it, and we got funded to create dairy animals for smallholders. So those dairy animals in sub-Saharan Africa are really a bank account for these smallholders, and if we're introducing Holstein genetics, which everybody there wants because of the milk yield, we want to make those animals thrive in the heat conditions and be able to withstand endemic disease, something that Holsteins are not very good at currently without this gene editing technology. So this could really advance the output of protein relative to greenhouse gas, which is really in inverse to where it is in the United States as far as output. So we've taken these Holsteins to adapt them to tropical systems, and we did that by editing 4 different loci, either simultaneously or after a couple of different editing treatments. So we put in the heat tolerance, something that Holstein doesn't have naturally. Trypanosome resilience, these are alleles that we identified in West African cattle that withstand bites from tsetse fly that gives them a disease called nagana that's very deadly to Holstein. And then also making them more resilient to TB by putting in a zebu allele at this gene called Marco. These animals are being registered by the Holstein, no questions asked. I did a lot of consultation with Holstein in 2016, and they saw the value of this technology, especially polled. They were quite actually angry at the multinational breeding companies for not putting more emphasis on putting polled genetics in, which has been done since then. But they saw this as a way out of having to dehorn animals. So we have no problem with them registering these animals, accepting these traits. They just track them in the pedigree. And really, we're not intending these multiplexed animals to go through US regulation. And so we can collect the germplasm in the US and we can export it as long as the country receiving it have regulatory approval. So for us, this is a US company using US genetics and exporting to emerging markets. That's the business opportunity. So we've already created 5 different sire lines for the Holstein. This is just a portfolio of those animals, the most recent one being born a couple months ago there, Arthur. He's quite a good looking calf. And the first 4 animals are already in stud. Next. We've also created 6 females that represent 4 different genetic lines. So the 3 different lines there on the bottom, all of those have either 3 or 4 edits, and then one of our cell lines actually produced 3 different clones. So some of these cell lines, even in the bovine embryonic stem cells, have differences in the rate of producing live animals that are viable. Next. As part of the Gates project, we also the goal is to really create a crossbred animal, a Girolando, so we did editing in gyr. So what would you edit in gyr for a tropical market? Well, zebu animals are completely susceptible to trypanosomiasis, so we put in alleles for that. And then we also put in a Holstein allele for improved milk yield in the gyr, something that they don't have in their population currently. And then this is, of course, our goal is to create Girolando animals, super Girolando, with these edited traits. This is just a photo of conventional Girolando, but this is what the Gates Foundation wants the smallholders to be able to obtain and just pull these heifers off the shelf every time they need a new animal. Next. So how do we get to market? If we've commercialized our ability to standardize the process for making these gene-edited animals, we have to prove it not only to the regulators, but to the interested parties in the value chain. So Dr. Beaver is going to go over some of this, but I just think it's important that you understand right now in the US with the FDA, they categorize our animals based upon what their intended use is and what type of IGA they have. So any animal with an IGA or an edit is categorized. The IGA in the animal is the regulated article. So when they first came out, they talked about the animal being a drug. They've completely backed off of that position, and the IGA is now the drug. Category 1 is basically rats and mice. They don't regulate those at all. They don't care about the animal welfare of the rats and mice. They don't care if people sell them. But if it's a food animal and it's experimental, you can qualify for Category 1 as long as it never enters into the food chain. You don't have to actually file or disclose to FDA to do that work. If you intend to sell or commercialize, you have to consult with FDA. So our choice has been to always file a VMF first before an INAD, because a VMF allows us to possibly be categorized as Category 2, which is a much less arduous path to get to commercialization, because they require a lot less scrutiny of the animal. And so why is that? Because we're introducing traits that could have been introduced through conventional breeding. So slick is one of those examples. It could have been done by crossbreeding. What we do have to prove is that there's a history of safe consumption, which there is with all the Criollo cattle in the world, that it's good for the animal well-being. That's already proven because we know it provides heat tolerance. So we can make the claim of heat tolerance without having to prove it out. We just have to prove that there's no off targets, because this is the area that really, if you think about what FDA is doing, they're writing briefs because they know there's going to be litigation from activist groups once they approve these animals. And that litigation is really what they're preparing for. So they want to be able to stand behind their decision and say, oh no, we've already looked at all of that, that's not a problem. By the way, we as animal breeders have never said off targets are a problem. That's a problem with the human biomedical community because you, like Allison stated last night, you can't have off targets when you're doing therapies for somatic cell gene editing. We're doing germline editing. There's germline mutations all the time, as she stated before. These off targets are going to be just like those. They're usually not going to have any effect. And if they did, usually the animal's not born. Or if it is born, you can notice there's a problem and you're never going to take it to market anyway. So they're regulating something that we as developers are already regulating. We just have to prove to them that we know what we're doing. And part of that comes from you guys talking and speaking up to them and telling them what kind of things you have in place. So the first time we went to the FDA, they didn't even know what CSS certified semen was. We had to explain that to them. So you guys already have regulations in place for how things work, import, export. FDA has no idea about any of these activities. They know now because as part of our consultation with them to get through regulatory, we have to educate them on all this stuff. And it's not easy going. So here, just showing the 3 different categories, you can go ahead and really, for category 2 or enforcement discretion, the timeline is supposed to be 180 days. So is it 180 days? Well, they try to stick to that, but the problem is as they're still learning this process of how they're going to regulate, they ask for different data sets to confirm what our initial data sets say, and then that 180-day period starts over. So at some point, they'll actually be able to stick to 180 days, but until they know what they want, 180 days is not reality, but it's definitely less than 2 years, I would say. If you provide all the data they want and they can prepare their legal brief in case something happens, you'll get through probably in the 6 months. For the INAD, I think it's still a bit arduous, especially for the BVD animals that we made with Clay Center, Nebraska. Unfortunately, even though we're just making several amino acid changes, we believe this will be categorized for a drug approval, and it takes 3 to 5 years. You still have to prove out that there's disease resistance in the next generation and the next generation. And it costs a lot of money to get through this process. So, will they back off of this? We're working on trying to get edits like BVD or like the PERS resistance by the deletion of exon 7 and CD163 to go back to being enforcement discretion rather than being an INAD. I think, if you're putting a transgene in, maybe INAD, you'll never escape that possibility unless you have a segregant that doesn't have the transgene. Next slide. So here's some of the animals that we have commercial allowance for. They're both black-red carriers. They have mosaicism for slick with the bull, and we have a complete homozygosity with the female. We've sold semen into Brazil, and this just shows the difference in the time period for the regulation. It was 2 months in Brazil. It actually took us longer to fill out the dossier, which is just answering questions as to whether or not it's GMO, which it was shown to be not. And then it took greater than 6 months to get this enforcement discretion in the US. Next. We've also got non-GMO determination on our first slick Holstein. His name's Diego. He's already been collected. We've actually contractually sold 500 straws to a breeder in Brazil. We're going through regulation in Colombia. Once those 2 countries have cleared them as non-GMO, we will go ahead with approvals in Nigeria and Kenya, who also have a system very similar to Brazil, Colombia, and of course it's based upon the Argentinian system, which is very similar. These are some other animals that are pending decisions. We've already submitted applications in Brazil for the other 4 females that we created from our initial Angus embryo injection project to make slick. And then we have a second slick bull that's at Transova right now. He's still not at collection age, but he'll be moving there soon. We also have 2 bulls we collected on Angus in Texas that will get approval. We're hoping to get FDA approval for the trait by the end of the year. But we still have to go through the process of proving that off-targets are safe that we have in some of those animals. So other factors to get a market. For us, we still see breeders or breed association approvals as very important. The value of the trait, it has to be sanctified by the breed association that there's actual value. Otherwise, there's no reason why you would approve it. I think you're concerned about traceability and potential labeling that comes with it. You do not need to know all of the things that were in the regulatory package. That's what the regulators are for. And then export of genetic products becomes an issue because some countries, they need the breed association endorsement or the pedigree and actually to import that semen into a country like Brazil. So you have to show the genomic proofs are in the top 50% for some of the traits in order to be allowed to import it. That's also true for Holstein. I think the biggest thing we're still wondering about is acceptance by the downstream value chain. Post-regulatory decisions on labeling are determined by USDA, and right now you don't need a label if it could have been done by conventional crossbreeding to bring in the same trait. Export of food products, I've consulted with the ministers of agriculture in Argentina, and they said, well, we don't really want slick Angus because we export all of our beef, and in Europe they won't accept it because they'll see it as GMO. So things like that are issues that have to be talked about and discussed because there are anti-biotech markets like Mexico, which is trying to ban GM corn right now from the United States. And so consumer acceptance, like Allison said yesterday, I really don't think that's the issue. That's kind of make-believe. For them, the issue is always price and quality. You have your activist groups, which represents maybe up to 10% of the population in the surveys that have been done. And it's really them that the FDA is afraid of in the litigation because they have a history of it. And just to show you how crazy they are, I put up this cover from the Friends of the Earth right before Australia came out with the decision that if you just break a gene, it's not regulated as far as using the genetics. For the food, that's a different matter. So they wrote this big 70-page document saying that Monsanto was creating monster beef. Not true. Okay, next. So I would say our experience has been commercial deployment is challenging, but it is possible. It takes a lot of work, and slowly but surely it seems like the tide is turning. It's really hard being out on the front end of this technology as we're the pioneer trying to bring this to market. I think the technology has demonstrated and will continue to demonstrate our ability to match genetics with environment and management to improve animal well-being and animal health, which are key factors in the carbon footprint for animals. I think one important thing that we're learning in the past month is US regulators, particularly the FDA, are open to learn from the industry to better align with the constraints of conventional production systems. So what does that mean? Our animals are not around forever. We move on to the next generation for genetic improvement. They have to understand what our systems are in order to feel that pressure that if they don't move quickly on some of these regulatory decisions and actually have reasons why they need to go through this process they do that's a little overbearing and much higher than the actual risk, that this technology won't be used. We'll just move it somewhere else. So I think right now, public funding opportunities, I've seen comments on grants. Professors write, you don't need to be funded because this will never make it to market. That's crazy. If we don't have R&D going on, the companies can't bear all of that. New traits and new methods need to be discovered by academia, and then those ideas need to be spun out and licensed to companies. Private funding is also troubled because in general, venture capital doesn't understand animal genetics. They don't understand the power of how genetic improvement can make animal production more sustainable, reduce carbon footprint. Our messages are not getting to them, and when they go back after I give a pitch and they try to decide whether or not this technology is something that's beneficial compared to seaweed or vaccines for methogens, they decide that it's much simpler for those solutions, even though there's a lot of pitfalls there, because they just don't understand how you're going to get the return on the value from the genetics. And they're right about one thing: there's a long generation interval for return on investment, especially if you're going through a regulatory system that's unclear. Next. Last slide. So just thank you for your attention. I've acknowledged a lot of our collaborators and partner network, and hopefully this stimulates some discussion later on for the panel. John, I'll turn it over to you.
Afternoon. The beauty of following my three colleagues is that they've captured the vast majority of the topic here, and I'm just going to reiterate some of that information. Oh, we're here already. What Mark asked me to talk about is maybe a little bit outside what I do every day, and it's the FDA regulatory process that has been mentioned here several times already this morning. So next slide. So I want to go way back in history, and I'm going to give an opinion here, and my colleagues here can agree or disagree, and that's what the discussion is for. A lot of this regulatory process has started quite a while ago when there was acknowledgement that biotechnology was going to have an impact on what we do. And so in 1986, there was this unified framework for biotechnology, and at the time, the regulatory agencies were USDA, EPA, and FDA. Again, this was recognition that biotechnology was an up-and-coming thing, and implementation of that probably required some type of regulatory framework to make sure that we didn't make a lot of mistakes. The second part here is what some of my colleagues might disagree with here, is that I think, so I have a message of a little bit of hope, but probably a lot of skepticism. Part of the reason I think, because besides some of the unknowns that we just talked about, that we've not moved forward in this regulatory process is that the realization that a lot of this is very political in nature. And so a lot of the progress, particularly in the FDA regulation of IGAs, is what we're calling them now, but way back when, genetically modified organisms, there's been really no push. And I think probably we're on the verge of assistance from political or from administrations in maybe making this or allowing this to happen. Allison showed a really nice slide last night on where these things are happening around the world. And she mentioned at the bottom of that graphic, there was this really long extended bar associated with country China. You see here Executive Order 14081 is a Biden administration executive order. And what that executive order is a recognition that these biotechnologies have a place in U.S. competitiveness worldwide. And that if we don't get our act together, not in several areas, but if we don't get our act together, we're going to lose that competitiveness. And so that's the message of hope, is that right now there is an administration that sees how competitiveness could be permanently, I think, damaged if we don't move forward on some of these things. And so I think that's where we're seeing some movement finally in regard to what the FDA regulatory process looks like. Next slide. little bit of problem because the rest of the information that I'm going to tell you, or I'm going to summarize for you, is that URL that's at the very top of that slide that none of you can read. Well, in fact, the animation is not even working right. So go ahead and hit it again. I don't know how that's backwards. What we're talking about is these intentional genomic alterations. So let's start first by, it's been mentioned several times, we're no longer in where we're going to call them GMOs or GEOs. The label that we talk about with USDA AMS is bioengineered, not genetically engineered, but bioengineered, or BE. But we're now defining these as intentional genomic alterations. I'll show you something here on the next slide go back. Yeah, okay, go back. That was right. No, backwards. There we go. Just keep it there. This definition now is kind of a overarching global definition. So FDA has now made this intentional genomic alterations in animals category. And if you read this paragraph, which is on the front page of that website at the top, maybe I can get Mark to circulate that to all attendees or something. It's going to be very important when we get a couple slides beyond here. But basically, this paragraph defines an IGA as all past technologies where we could make modifications to the genome, and potentially all future technologies. And so this is what we're going to refer to these from now on as IGAs. The next slide. Yeah. Anyway, the reason why the FDA banner was at the top of the last slide is I talked about the coordinated framework, but FDA, by legislation of the Federal Food, Drug, and Cosmetic Act of 1938 is why they have the regulatory oversight of IGAs. Okay, and there's been an argument, long-standing argument, as to why we can't go into that Food, Drug, and Cosmetic Act and remove that regulatory oversight from FDA and perhaps hand it to USDA. And there's been a lot of resistance to that because once you open legislation, it turns into a nightmare for everybody trying to stick things in there or get things passed along with it. So for the time being, FDA is still going to stay in charge of this. So if you were to scroll down that web page, you'll find this information on what are these guidance for industry, GFIs. There are two of them now. There used to be only one. Go to next, just click next. This is a long-standing document. This document was first published in 2009 as Guidance 187, and that was in response to genetically modified organisms and the idea that FDA was going to regulate them. It was later updated when new technology, so that we've talked about CRISPR, we've talked about, this is a little bit before CRISPR, but we talked about CRISPR, the zinc fingers, talons, these nucleases that Allison talked about last night. Those discoveries happened in 2010, 2013, and beyond. And so in 2017, FDA modified this guidance to include those technologies. The final guidance, which is marked final, and that was on that, or it'll be on the next slide here, was actually issued May 1st of this year. And it's supposed to be this comprehensive final guidance on how we're going to treat these things. The second document now, though, is Guidance 187B, and it discusses the approval process. And I'm not going to spend a lot of time on that approval process, but I am going to share some opinions, just like my colleagues, on some things that are still problematic with that guidance. Go ahead. this is 187A, and again, you can find that in one of the URLs on that homepage for FDA. The red box in the center there, it is a final guidance. There probably won't be any additional updates to that. If there are other guidance issued, it probably won't be 187A that is modified. So it is a final guidance, and they call it a risk-based approach. And Tad went over this real well, but I'll go over it again briefly. Next. So again, Category 1, you guys aren't concerned with Category 1. These are modifications that are made in lab animal species and other species that are not part of the food chain, and so we're not concerned with those. Next. Category 2 are the ones that probably that we're talking about here today, or for the most part talking about here today. They are food-producing species. The things from this risk-based approach, 3 guidelines: history of safe use in animal agriculture food production. That would be something like POLD. We know POLD's been around forever, right? So there's a history of use of that genetic variant that says it's safe for use. Second, theoretically achievable through conventional breeding, resulting in no change in food. Here's where we start getting into that's not a problem. Theoretically achievable in conventional breeding. I'll just give you some timelines. That's already been mentioned a couple times. Every generation, there are spontaneous mutations introduced into the germplasm of our animal species, ourselves, okay? And so the question is, how long would it take by conventional breeding to achieve the same goal? Do we have to wait for one of the modifications or the DNA base pair changes? How many generations would that take? And so that's kind of an open-ended thing. But the idea is that if we waited long enough and we had put selection pressure on our animal populations sufficiently, there's probably no doubt that some of the modifications that we're making right now we would select them and we would identify them in our populations and then select for them, okay, through conventional means. The last bullet point is where we started getting into a little bit of problem. Other case, and Tad talked about this a little bit, is there appears to be a commitment, and this I guess another message of hope, there appears to be a commitment on FDA's part to learn from these review processes, to educate themselves and understand what they need to categorize IGA as Category 2. But go to the next slide. These are the dangers of other cases, and they're considered case by case. Is there a risk that the IGA poses to human, animal, or environment? The environmental risk is actually is a legislative commitment. FDA does need to follow the policy of the National Environmental Protection Act, and so there is some environmental assessment done here. If there's an unintentional release into the environment, is there any more risk than the non-IGA comparator? So in other words, do these differ from a competitive standpoint, or I guess a resource utilization standpoint, things like that? Most of the things we're doing now, we have absolute control and traceability, where we could follow these animals. There's no let loose in the population, maybe in other countries, but in the U.S. there's no, we don't have a lot of feral cattle populations in the United States. Is there concern over the disposal of the animals? Well, we hope that most of this is going to get in the food chains at some point in time. Again, this is kind of I don't know if we're making things up to record or what the deal is, but the point is that this is where this guidance, the decision whether or not you're Category 2 or you go into the Category 3 process and have to apply for, make an application for approval. There's still some ambiguity there, and that's what scares us, is that we don't know how the FDA is going to react to some of the information that we provide. And as has already been mentioned here, if you get put into Category 2 where you need to file an application, you're in for the long haul, and it could be expensive haul. Next slide. So what is the category review process? Tad mentioned that in theory it's supposed to take 180 days. What you need to do as a developer, that's what they call those of us that are working in this area, what you need to do as a developer is contact the FDA, Center for Veterinary Medicine, and file or initiate the filing of something called a veterinary master file. And once you get started with that, you provide the data that you have, indicating that there should be no risk. And they evaluate that data in their 180 days and then come to you with a decision of enforcement discretion or the idea or the fact that you have to make an application for approval. But as Tad mentioned, it's not clear what the sufficiency of that risk assessment data are. There's always this opportunity that they could evaluate it and say, well, what about this little area over here? You need to tell us about this risk. And then your clock starts over, okay? And so then we're kind of caught in the same situation, is that it's these extended periods of time where you're not making any progress. The upside here is that if you are granted enforcement discretion, then you can proceed through the necessary routes for commercialization. Next. This is the other guidance, and again, I'm not going to spend a lot of time on here. The important part with this is, and the reason why I think that we need to circulate the URL to all of you guys, notice that the red box in the center says this is a draft. So again, this was issued in May of this year. The reason why it's a draft is these things, the government does allow public comment and takes into consideration public comment before they make these final drafts. Down here in the bottom, you notice that we're not to July 31st, 2024 yet. That means that all of you in this room have the opportunity, through the mechanism described that submit comments online, to go through Guidance 187B. If you want to go to sleep at night, 10:30, 11 o'clock, get your copy of 187B and start going. About 3 pages in, you completely knock you out. Try to stick with it. It's about a 30-page document. But the idea here is that you guys are in control. You guys have some control as a public to provide your comments. As individuals, there are a number of representatives here from breed organizations. This is where we have the opportunity to put pressure on whether or not we're listened to or not, but we have the opportunity here. So by July 31st of this year, try to get through 187B and make some comments on it. Next slide. Next. I'm not going to go through all 30 pages of 187B. I'll tell you my concern with 187B is that we have pushed for years for this risk assessment-based evaluation versus what we call a process-based evaluation. Process-based evaluation is what FDA is used to. They're used to getting, having drugs submitted to them, and then what they wind up doing is they wind up collecting. So, for instance, in 187B, you have to tell them about your manufacturing facility. Okay? I don't know. I'm lost, right? You have to document. It's not a bad thing to document transport and things like that, but basically the record keeping becomes onerous. The record keeping and answering, all the questions that are involved. There's probably about a dozen different things that are included in this in these points of record keeping, but this is where it turns into where they begin treating them like actual drugs, and it's process based. How did you do it? What is it made of? And then data collection and this assessment becomes this onerous process that that we can't get through. Um, and again, it's open-ended, so there's always this iteration, like, well, here's what we want. And you give it to them, and then they say, well, yeah, but we need this, or we need this, and the clock always starts over again. So I think 187B is great, but we need to make this whole process risk-based and be less focused on process-based things, and hopefully we can get through this. Next slide. I don't know if there's anything left. No, there should be something left. This is very important. We've also pushed for many years for USDA to have some input on this process. We haven't mentioned it probably at all here, but maybe some of you know that APHIS is actually the regulatory body in charge of all plant modifications. So all the crop species that have been engineered are actually regulated and assessed by APHIS, a USDA organization. We think USDA is in a better position to evaluate some of these risks because of what we do in agriculture and the understanding of what we do in agriculture, and we don't have to re-educate things like the FDA. But along with these two guidances, there was a memorandum of understanding recently produced between USDA and FDA, and go one click. What this does, it doesn't necessarily give USDA necessarily any oversight, but it sets up a framework of coordinated communication. And I think that this is promising. The more promising part is that in the end, if we do get to commercialization, we have the opportunity. You have to do this independently of this memorandum anyway. But realize that some of these judgments, whether or not, when we start producing these commercially and they begin to go in the food chain, whether or not there's any impact. So there's the Federal Meat Inspection Act, which provides guidelines to the FSIS, and of course those are the entities that are responsible for meat inspection and making sure we have safe food supply. And so you'd think that they should be part of the regulatory framework. And so this opens up this opportunity for them to provide input and feedback, and gets, and hopefully gets things moving. I think this is the end, so just next. Should be blank, probably. There we go. Okay, that's all I got.
So we have some time for questions. I want to thank all of our speakers for their presentations. Do we have any questions for our panelists? So John, you touched on one question that I had throughout the different presentations. Gene editing, genetically engineered, precision breeding, IGA, bioengineered. And I think as an industry, it's probably good that we're unified on a front in how we take this to our stakeholders, consumers, and how we talk about this technology. Is IGA the preferred acronym? Is that the preferred name? Panelists, your thoughts on that?
So I'm not sure it would have been the name that I would pick, because it's not. You guys, from a working standpoint, intentional genomic alteration is not tethered to your everyday life, or it's not a terminology that is obvious to you. But at the same time, has been talked about, is this has been a 30-year or more process in which the word GMO, for instance, elicits a certain response from certain groups or certain individuals. And so now we find ourselves not being able to use that terminology because at the set of a discussion, so we can have discussions, right? But the first time, when you say, well, let's discuss GMOs, and you have 10% of the population that are fairly, anti-GMO and active in that regard, all of a sudden the discussion stops. And so we wind up changing these terminologies over time in order to avoid some of the historical issues we've had with them. IGA wouldn't be my preferred choice, but I think it's what's defined now by FDA, and so I think we have to kind of go with it.
Go ahead.
All right, I have some thoughts. I think it's a disaster because we had an opportunity with genome editing to disassociate GMOs from genome editing. What the FDA has done is put them all in one big cluster basket together, which is exactly what the activists are trying to do. They're trying to conflate genome editing, which is often tweaking naturally occurring variations, which is analogous to breeding, with the GMO regulations of genetic engineering. It's an absolute disaster. What Brazil and Argentina have done is they've said, actually, this is not GMO. It's different. And that's the point we've been trying to make. But what the FDA has done is put them into this weird category. Intentional genomic alteration sounds like something Frankenstein does in his spare time. And I think it's horrible. And so I do not agree that it's a good thing, and I think it's actually going to... And what's frustrating is we've had 35 years of public communication around GMOs. It hasn't gone well. We didn't learn. And so when they just conflated those two together, it's like they just ignored the history of what happened and didn't learn how it could be communicated better. So I do not like that term, and I think it's not good.
Questions? So I'm quite confident that FDA's probably not been mentioned more in a cattle breed, cattle talk or a presentation. You talked about the 187B. What, as a unified group, what kind of comments do we need to be making in response?
You need to be talking about how your systems are doing genetic improvement over certain periods of time and how you see their regulatory process is not aligning well with being able to integrate the use of these tools into your systems. Cost is an issue. If it costs so much to go through this process, how do you make the money back to generate revenue while still improving the breed with something relevant as far as genetics go? And then just being able to defend the fact that showing durability is silly, because that's from the old technology where transgenes used to pop out of animals. And there's enough data on Mendelian genetics that you don't need to prove durability. These are all just things that the activist lawyers are going to argue that FDA didn't do a thorough enough job in regulating, and that's why they request it.
That covers it.
Other questions?
I guess the other point I would make is that this is making America not competitive relative to your major competitors, and they have a better system, and it's going to move to those countries. And I have no doubt China and Brazil and Argentina will have access to this technology, and we'll be sitting like Europe on our hands.
By the way, Australia is changing theirs to be more like
Yep.
Argentina and Brazil as well.
Right.
They want polled.
So relative to genetic evaluation, I mean, we're going to move forward with, seems like hopefully these qualitative traits as we get into the more of the polygenic edits. What research needs to be done to allow these traits to go into genetic evaluations? I mean, it's kind of a little bit unknown, and how we handle those type of animals if we get to them. What kind of research do we need to be doing?
So I think at least with the edits that we're doing now, and I think you're talking about, maybe potentially doing some polygenic work in the future. I think we're probably more 3 to 5 years down the road for that. Maybe not. I don't know. But a lot of the things that are being considered now that I hope fall into these category 2 risk assessments are kind of low-hanging fruit, and they're major effect genes. And if those major effects have an impact on overall performance for any of the parameters or any of the genetic merit estimates that you make, your genetic evaluation will identify those quite readily. And if you're using genomic selection tools, and there's a introduction of an IGA for let's say increased lean growth, you'll see it. You'll see it in your evaluation. There will be no doubt about it. So, at a certain point, you'd expect some of these modifications or alterations to be included on your genotyping arrays. That adds the aspect of traceability, which may or may not be completely necessary. But you have the ability to trace these things and actually look at what it's doing to your genetic evaluation. But I think that for many of these things that we're talking about now, they have quite significant effects. And when you see that, we have situations in many industries where, I'll give you an example in pigs. It's a mutation that increases lean growth, happened probably 300, 350 years ago. If you look at the pigs in the 1940s and 1950s where we'd had lard-type pigs, the allele frequency of that mutation, that naturally occurring mutation, was quite low. It was 15 to 20% in the U.S. germplasm. Today, it's over 90%. It's over 90% because we select for lean growth, and we changed the type of pig after the 1950s, and we pushed from a selection standpoint, we drove the allele frequency of that mutation to increase almost to fixation. And so you guys will recognize it in your evaluations, is my opinion.
I'll just speak about the case of slick. We've used crossbreeding for heat adaptation in the Gulf states and definitely in Brazil, but I think what is going to be exciting is there's research groups using our semen. Our bull throws both normal and slick animals, and so you're going to be able to do a lot of half-sib comparisons to see the differences in performance of when you remove heat stress from the Angus genotype. So that's going to generate a lot of different papers and what its effects are on health, possibly fescue toxicity, and even tick resistance. Good.
There we go. Being a complete neophyte in the area of regulation appears to me, just sitting here listening to you all, this is going to have to get political. There's going to have to be the political will of somebody uh, to move it from FDA to USDA, which I think you all are advocating. Do you all see that as a possibility in the future of being able to accomplish that? Now, I understand that if you go to doing it politically, some senator from Massachusetts or Delaware is going to want to plug in his pet project into that legislation. But it appears to me it's going to have to get political to get it, the process that you all are up against for approval, you're going to have to get it moved to USDA. Then you're going to have to hope that they've got the scientists there that know what the hell they're talking about and can understand it. Apparently they would have, because they're already doing it through APHIS in the plant side.
So when Sonny Perdue was the Secretary of Agriculture, there was actually a notice of proposed rulemaking that was introduced to move agricultural edits for food purposes from the FDA over to USDA. That was submitted, I don't know, maybe a week before the election, something that was very difficult timing. And as far as I know, that is just sitting dead without moving forward. Yeah, so, well, the MOU is, according to John, is the outcome of that. That MOU is fine, but that's not what this notice of proposed rulemaking was going to do. It was going to transfer the entire thing over to USDA. So I agree it's political. I will say that, interestingly, feed additives for reduction of methane, so things like seaweed, are also regulated by the Center of Veterinary Medicine as new animal drugs. And that is blocking them coming to market. So they're having exactly the same problems that we're discussing as it relates to these feed additives. And as a result of that, there's actually been some congressional action to move that from being a drug to being a feed additive. And that actually had some senators, and I think it was a senator from Wisconsin, if I'm not mistaken, that did that. To me, there's a logical connection between these two things. They're both trying to reduce the environmental footprint of agriculture, and they're being held up by this new animal drug paradigm of the Food and Drug Administration. Unfortunately, they didn't get married together, but that's actually stopping all approvals of feed additives in America at the current time for reduction in methane emissions, which is a goal that I think this administration wants. And so there is some potential synergy there, but that one took actual congressional action to get it moved, not that it's actually happened yet.
Just maybe another comment. I think you're correct in terms of does this need to be political, but there's some fundamental issues that normally in commerce, I'm a capitalist and believe that things follow a dollar, but in politics, it tends to follow a vote. And so there's people sometimes that will avoid some of these topics in some of these areas because they'll maybe step back from them. And I think it takes a period of time. Plus, the second component is regulators regulate. And so FDA has authority for this position where they're at, and they want to maintain that. And so there's some fundamentals that make this go more slowly than we would like to see it. And because of it, then it really slows down investment and ability to move some of these things forward, and you get concerned about where's this go in the future, and then global competitiveness, even global harmonization on these in terms of the movement of food and genetics.
Yeah, I think the time to move it to USDA is past, in our opinion, and we have a business to run, so all we can do right now is do our best to educate FDA that there's not as much risk as they're perceiving there might be, and just their approach to going into it to be more like the other countries as far as being able to bring it to market.
So when we look at our genes of interest, it seems like we keep hearing about the same five, at least when it comes to cattle, myostatin and BVD and polled versus horned. So looking into the future quite a ways, 25 years from now, what genes of interest do you think we're going to be looking at? I'm assuming they'll get more complex, and kind of how do regulations change as we move into those more complex? Once we take care of myostatin and polled versus horned, we can only get more complicated from here, and I'm guessing the regulations probably will too. And how as commercial cattlemen and our seed stock operations, how are we going to deal with that?
For us, there's a lot of adapted cattle that could use a lot of a genetic improvement relative to puberty, precocious puberty. On the dairy side for adapted animals, oxytocin release to be more like Holstein. And then on the beef side, improving tenderness and marbling in those breeds without having to do the crossbreeding. So there's a lot of traits that we're working on. We believe we have some of those solutions. I didn't talk about them, of course, because it's still in our R&D pipeline. And then there's a lot of things that still have to be discovered through the genomics works that's being done in different academic institutions. So we maintain partnerships to try and stay close to what's going on.
Probably a bit sacrilegious on a panel about genome editing, but conventional selection does a pretty good job with many traits that are polygenic too. So I think it's a synergistic complement. That we still do a good job with conventional breeding on many of these traits.
Well, we're a little behind schedule. Got one more question. Dr. Weber.
Thanks, Shane. And I'll try and make this quick. One of the issues that many breeds and boards of directors of those breeds is dealing with is the policy side of how do we manage and trace genome-edited animals through the pedigree structure at the Breed Association. And John, I appreciate your comments relative to genetic evaluation. I share your view that we just put the mutation or the change on the panel, genotype it, move on. What other policy components would you recommend breeds consider? My presumption, since these are naturally occurring variants in the population, there's no other IP issues to deal with directly related to the sequence, but potentially in the process in which they get developed and so forth. So help us a little bit think through, and I know there's, I'll carry some message to BIF, of course, but other breed association staff and board members in the audience, what direction might you give us in that regard?
So we've had quite a bit of interaction with different breed associations. I think from our perspective as a business, and we're like the only ones out there pushing this right now, but there's going to be more groups. You need to decide as a breed association what traits you would accept prior to them even being approved by FDA. And you have to remember that each developer has to go through the approval process. So if I get SLIC approved in the United States as Excelogen, that doesn't mean that company B can do the same thing. But you have to decide if that's a trait that you want, whatever trait it may be, and before it's regulated, so it's kind of a pre-acceptance. That way, if a breeder wants to take the risk at going forward with that trait to create some animals before the regulatory approval, there's at least a breed association backing that this is something they want to introduce in. And then you don't have to give a final approval until the regulators are done doing the regulating. But you have to decide which direction your breed's going to go and how best to use this technology to complement what you're doing now based on genomic selection or current EPDs.
Well, let's thank Dr. Mark Johnson for pulling off getting all these great panelists here. Thank you guys for your time. Really good job. We have a little break.